So the first step is this, where it'll add, right? CH2 minus. Okay.
Yeah.
And this is CH2, right?
Yeah.
Okay, let's see what we can do. So now this comes back here, and this bond moves, and this goes here, and this goes here. Now you got it?
Okay, yeah, so yeah, I think I got it right now.
Right?
Yeah.
Yeah, this is tricky one. But yeah, this is how it is, huh?
Yeah.
Okay. Great. And then, did you do these? No.
No, so we had, I think the homework question, I think was 85 or some, or one of those.
Which one?
So 1 second, I'll just check which one it was. I think,
Okay, you send it to me. Send everything now. Okay, and
yeah,
then ask. Don't waste time in the class. 93. Start doing. Okay, we have so much of time. Okay, you can message me anytime. Okay,
yeah,
you just send the homework, and wherever you are stuck, just message. Okay, do this now. And in the class also you can ask if you are. But keep everything ready. Huh?
yeah, so I have all the homework.
Okay. No problem. In the first one, we have to protect the alcohol group. So this you can skip because we did not do the, but there are like, I mean, there are a lot of ways to protect this. Okay. And after protecting this, we can just use Grignard reagent and get this, right?
Yeah.
Tertiary alcohol. Okay. And the same thing is the for the B, I think.
B also OH group needs to be protected.
OH needs to be protected, yes. Go to C, and then I think we are almost done. C, I think you should do. C, yeah. Yes. See you too. What did you have for lunch?
So I had rice and yeah, I had curd rice.
Curd rice. Nice, nice. You are vegetarian, right?
No, sir.
Okay. So what do you prefer, mutton or chicken?
Yeah, so chicken only.
Okay, not mutton, huh?
Yeah.
And you prefer fish food?
Yeah. So for saying getting how to directly attach OH group, but I'm not getting on how to attach with.
See, first we have to protect the ketone, right?
Yeah.
And after that, what do we do? If I tell you that it's done, think. See, think backwards. See, whenever you have to add two carbons and make an alcohol, okay, always think of an epoxide. Now
Okay.
try to do. And epoxide means that you have to convert this into something nucleophilic, right?
Yeah.
So what will be that?
Yeah. Yeah. So just thinking I'll do it. Yeah.
Will be Grignard reagent. See, first we protect it like this, huh?
Yeah. With bisphenol diol. Yeah.
Then we make this, huh? Then we open this, huh? Got it?
Yeah. Yes, I got it from here.
But write it. Okay, write and send. You have to send me without my saying every time, okay? You have to send it because that will build good practice, okay?
So after we make the Grignard reagent, only we add the epoxide, right?
Yes, yes. And then we acidify and hydrolyze and then everything open up,
Hydrolyze. Yeah.
right? Yeah. Yes. Okay, I'll do this homework. Do this here. 6/7/25. Think backwards, huh?
Yeah, yes, sir.
Any idea?
Yeah, so I thought first I make a ketone group and then
Yes,
add,
cyclohexanone will make, and before that it will be a cyclohexanol, right?
yeah. Then from cyclohexanol,
It
uh,
will be cyclohexyl bromide. Huh?
sorry, yeah, and then tautomerize to hexanone.
From
Then
this Br2H nu I can get. Okay.
yeah,
From here I have to get OH. Huh?
yeah, and then last step after from cyclohexanone, I'll treat with Grignard reagent.
Yes. But how to go from here to here? Br2OH.
So with aqueous KOH.
Yeah, that's one way, but there are a lot of problems. So because it will only undergo SN2, right?
Yeah, I thought with SN2 we can put aqueous KOH.
But SN2 it will aqueous H2O is nothing, it is only H2O. So with H2O it will have problems. So first we treat it with this. See, and then it will become OC double bond of CH3. Ester, right?
Yeah, and then okay, then we can treat with OH minus.
Then I can hydrolyze it, right?
Yeah,
Then I'll get OH and then I treated that. Okay?
yeah.
Okay. So I think we are at the end now. Okay. A and B. After this, we'll start a new chapter. Huh? What's going on in school? Still alcohol, phenol, ether.
Yeah, so they just completed.
Completed. Oh, finally,
Yeah.
huh?
Yeah.
And after this, they are starting what?
So after this, I think they have to start carbonyl compounds.
Okay. Then they'll mix it up, huh?
Yeah.
Good. We'll do reactions at alpha carbon now. No, I think we'll do we'll do one chapter today. No, 17 is alpha carbon, right? Yes. Yeah, after this we'll do alpha carbon. Okay.
So here in B part, I'll tautomerize it in the very last step only, right?
Okay, they'll ask you directly the products for this, huh? Okay. So it will be like, let's say this is the first carbon. So this is the first carbon. No, on the CHO, yes. This is the first carbon. This is the second carbon. This is the second carbon. Let's say this is third, fourth, fifth. Let's say this is third, fourth, fifth. And from 2, 6, 7, 8. Got it?
So A part I'm getting stuck, but B part I got.
A, you got it?
So I got B, I'm not getting A.
You are not getting A.
No.
Okay. But if I ask you to write the product, can you write the product?
Yes, I think I can write the product, but I think I have confusion. My confusion is when they're opening the chain, both the chains.
See, the first, forget about this. This is C and it is
Yeah.
attached to these two alcohol groups, right? It's
Yeah,
an
so
it's an
OH
it's
will
an
attract
acetal,
that.
right?
Yeah. Yes, I got that part.
And we can break it and we can get the product, right?
So,
See,
but how exactly is it breaking?
see, it'll break like this. This is the carbon, and we will give it 2OH, and we will give this. This will get OH. And this 2 will get 2OH, and
Oh,
which
okay, and then the aldehyde will be there. Okay, yes, I got
got
it.
it?
Yeah, now I got it. Yeah.
Okay, always number. You have to find the structure. So that is how why I said this was carbon one, and
Yeah. Yeah, I thought that was the other carbon, the original OH.
this is 1, 2, and then 3, 4, 5. So I can say this is 3, 4, 5. Same structure, and then 6, 7, 8. So this is 6, 7, 8. Got it?
Yeah, I got it. Yeah, sir.
Okay. Okay, the mechanism, I'll send it to you, but you can try at home. Okay. So mechanism, it will start. First, a protonation will take place. Okay. You can start like this. Oh, let's start this. You can start mechanism like this. First, you can protonate any of this. Let's say you protonate this.
Yeah, then
Then the lone pair will assist, and this will open.
open up. Yeah.
Oxonium ion form. This, and I have this OH, and then water attacks this carbon. This opens up. And I'm losing the proton in single step. Got it?
Yes, I got it.
And just because I have to LZ. Then this protonation takes place. Then this. Got it?
Yes, I got it.
I'll just draw it the other way. So it will be now double bond O, H plus, this plus. And it'll lose the proton, right?
Yeah.
Okay. This is another most important chapter, reaction with alpha carbon. Okay. So paper mulberry tree. So 15 aromatase inhibitors they are used for the treatment of breast cancer for this. Okay. So now we are going to see how things are going to be. See, this is very important. Okay. This is the most important chapter for JEE Advanced. Okay. So we'll see. See, first how it is starting. You can see there it's written. Okay. Then in page 823 they have explained. Okay. So what is happening is we know that nucleophilic addition takes place, right?
Yeah.
That's the first thing. But see, they are saying that if we employ a strong base, okay, the carbon next to the C double bond O is called an alpha carbon. So this is an alpha carbon. Okay. So the alpha hydrogen is acidic. So a base can be employed which can pick this alpha hydrogen. Why this alpha hydrogen is acidic? Because after taking out this proton, this will be resonance stabilized, right? Got it?
Yeah, so just going through it one.
This proton it picks alpha hydrogen, it'll a negative will come here, and then this can be stabilized by resonance. Huh?
Okay, yeah, so it has a negative charge there, yeah.
Yeah, it has a negative charge, huh? Because the proton has picked up the H, right?
Yeah, yes, sir.
Okay, so that is the thing. So and after this proton has been picked, this has become a nucleophile, right?
Oh,
Right?
okay, yeah.
Okay, that is the whole game. That's it. After picking up the alpha hydrogen, it becomes the and a nucleophile. See, acidity of an alpha hydrogen. We know that this ethane is pK is greater than 60, right?
Yeah.
And so the hydrogens which are bonded to sp3 are not acidic, right? But look at these hydrogens, they are also bonded to sp3 carbon,
Yeah.
but they are quite acidic. Why it is like this? Again, I told you the reason, right? For aldehyde and ketone, the pK value is 16 to 20, whereas for the ester, it is around 25. The same as the
Yeah.
pK of the terminal alkyne. Huh?
Yeah.
Okay. And there's some values are given for the, and you can see that the for NO2 group it is very less. Huh? It's quite acidic, right? And
Yeah.
2NO2 it is more acidic than a carboxylic acid. Okay, pK. Here also see if it is flanked by these two groups, it is fairly acidic. If it is one aldehyde, it is fairly acidic. Why? Because this proton, after we have picked up a proton, it can delocalize at two spaces. Huh?
Oh,
Right?
okay, yeah.
Okay. So that's why this middle proton is more acidic, right?
Acidic, yeah.
You can see that this proton is quite acidic, right? So this is the acidic pattern, right? And yeah, nitrile is not that effective as NO2 group, right? Okay. So in this case, we have delocalized electrons, right? So no stabilization, but whereas in this particular case, see, base picks up a proton, carbon gets a negative charge, and it is delocalized, right?
Yeah.
And electrons are accommodated on the oxygen than on carbon. So it is stabilized, right?
Yes, sir. Yeah, got it.
So again for the ester, this is the situation. Now the ester is that why it is less, because the oxygen is also delocalizing. So it is getting less time to delocalize. Huh? Got it? It is
Yeah,
not completely
okay.
free for it to delocalize because these are also delocalizing, right?
Oh, okay, yeah,
The
sir, got
lone pair
it.
of oxygen are also delocalizing, so
Localizing
they have
and
to wait
the
for their turn to
group.
delocalize and get stable. Huh?
Yeah.
Okay. Okay. So this is the question: why the pK of hydrogen propane is greater than any of the carbon, but less than that of. So propane is due to hybridization, right? sp3 carbon. Oh, they of the propene they have asked. Okay, for propene again we can delocalize, right? This is propene, and after delocalization we'll get this, and this is resonance stabilized, right?
Yeah.
So you can do this question if you want to. Okay, now see, this is 2,4-pentane dione. It's a beta diketone, so it is flanked by two carbonyl groups, right?
Yeah, yes, sir.
And if it is flanked by one ester and one carbonyl, then which will be more acidic? This will be more acidic because
Ester.
here again that it has to compete with this oxygen, right?
It's oxygen, yeah.
Right. So, so this is beta diketone, beta diester. Okay. And it's again same thing. It can, you have to do this as homework. Explain why a base cannot remove a proton from the alpha carbon of this of the carboxylic acid, because the base will remove the proton from here only, right?
Yeah, yeah,
It won't go to the alpha because it is much more acidic, right?
yeah.
Okay, now they are explain why a base can remove a proton from the alpha carbon of the NN dimethylethanamide, but not from the alpha carbon. Same reason, right? In the second and third example, the proton will be removed from the nitrogen, right? Hydrogen which is attached to nitrogen, right?
Nitrogen, yeah, he'll
Got
become
it?
a
Because it is more
separation.
acidic, right?
Yeah.
Okay, then the same thing. I think we should do 5. Okay. You can also explain 4 if you want. Yeah, do it.
So here I had wondered when we say alpha hydrogen of ester, it's a hydrogen that is directly attached on the carbon that's directly attached to oxygen, right?
Why for the first one?
Yes, I here the alpha hydrogen of an ester is the hydrogen that's bonded to the carbon, which is
Carbonyl carbon, right?
yeah,
See,
carbon.
for the alpha hydrogen is bonded to alpha carbon. So let us say I have this ester. So CH2, this is the alpha carbon.
Yeah,
Got
that
it?
is the alpha hydrogen. Yeah,
And
got
this is
it. Yeah.
alpha hydrogen. Okay.
Yeah.
This is so because the amide has more better resonance, right?
Oh, okay. Yeah, yeah, yes, I got
Now
it.
you remember, right?
Yeah, because the amide lone pass through better resonance and that.
Yes, right.
Yeah, sir, done.
Okay, so the first one,
So, first one I'm getting the third, three,
third,
four, one.
fourth, first, second.
Yeah.
For
With the
the B, we are getting first, third, second, fourth.
yeah, yes, sir.
For the last one, we are getting 3, 2, 1. Yeah,
Yeah, yeah, yes, sir.
3, 2, 1. Okay, you have to send me. Anyways, keto enol tautomers. See, this is keto, this is enol. Huh? Yeah.
Yeah,
See bottom. It's also keto. This is enol, right?
yeah, yes, sir.
Less than 0.1%. Now here, see, 85%. See, so normally it is less than 0.1% enol, but here we have 15% enol, right? Right?
So here only one of the groups have become email, right?
See here, yeah, one of the group has analyzed, right?
Okay, yeah.
0.1% is the normal, huh? Okay.
Yeah.
Why is it is so much?
Hydrogen bonding.
Okay.
Yeah.
Okay. It's written hydrogen bond, right? See what is that? Nice 6-membered ring, huh?
Yeah, yes, sir.
Okay. I'll use the pink. Right?
Okay, yeah, yes, I got it.
Cool, stable, huh?
Yeah.
So that is the thing. And here, oh my God, enol is more stable than
Oh, yeah,
keto.
because it's
Why?
aromatic.
Okay.
Yeah, yes, sir.
Got it?
Got it.
Right? Cool. Now explain this. Six.
So in 6 ounces is because in hexane it'll have lots of all the hydrogens attached to the carbon for hydrogen bonding, and in water it won't.
Sorry?
So is it because in hexane it'll have many more of the hydrogens attached to the in the alkane and for hydrogen bonding and not in water?
No, I did not catch you.
So is it because in hexane there'll be many more hydrogens for hydrogen bonding?
No, 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 no. That is true, but how that is going to affect anything, right?
Okay, yeah.
Okay. See, what is happening is that when we are uh, in the water, right? 2,4 pentane ion, right? So in the water, let's draw it blue. In the water, although this hydrogen bonding is there, but this this portion, the ketone portion can be stabilized by the hydrogen bonding from the water, right? Right?
Oh, okay, yeah, I got it.
But in the hexane, there is no stability like this for this, right? For the keto, right?
Yeah.
So all of it would want to go here so that it
So,
becomes
yeah.
stabilized, right?
Yeah.
Right?
Okay, yeah, yes, I got it.
Okay. So, yeah, that is that. Okay. Now ketoenol interconversion. See what is happening? We take a base. This is a keto tautomer. Proton HO minus base will pick this proton. We'll get this carbon ion. Okay. And this carbon ion it can delocalize. And again, O minus can pick up proton and we get an enol tautomer. So this is base catalyzed keto-enol interconversion. Okay.
Yeah.
How do acid catalyze occur? First the protonation occur, then H2O takes the water and the same thing happens. See, watch it, watch it.
So in base, first by forming nucleophile on carbon and here by protonating the water.
Yeah, right. It makes
Yeah.
sense, right?
Yeah, yes, that makes sense.
Right, because H plus is there, so acid-base reaction will occur, right?
Yeah.
First. So, and there is the base, so it will not obviously react with this, so alpha hydrogen is getting picked up. Okay, do this and send it. 7, 8.
So here for cases like E, I can automatize only one of them also for hydrogen bonding, right?
Yeah, now speak.
So for like E subpart and those type of cases, I can automatize only one of them and show a hydrogen bonding also.
If you'll think, you'll know which one to do. Okay?
Okay, yeah,
Okay. Do it. Don't be
yeah,
afraid of doing a mistake. Huh? See, you have to commit mistakes, Neha. Okay? That is the game.
yeah, yeah, sir.
Right? Because nobody learns without Elon Musk is doing so many mistakes. Only Indians are not doing any. Yeah?
Yeah.
Right? So that is how it is.
Okay, yeah, yes, sir, done.
Okay, send it.
Yeah, send.
Great. See, now the magic begins. See this base promoted halogenation. What is happening? Base is converting it into a nucleophile, right? As we talked about, it's a nucleophile, right? Alpha hydrogen is picked,
Oh, okay, yeah, yeah.
right? Nucleophile. And from here only, you can, if you want, you can, oh, here only we can say that this carbon attacks here and we get the product. But they have made the enolate ion and then it comes back and it's the same thing, huh? Got it? Check it, check it, take a while.
Oh, okay, yeah. So in the end, we're protonating the, I mean, we're taking the other H plus also and doing the same thing.
Yes, 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 right. And now this alpha hydrogen will become more acidic because the bromine is attached here and it will also start pulling a inductive effect, right?
Yeah, yes, sir.
Got it?
Yeah,
Okay, clear?
yeah,
Sure.
yes, sir. Clear.
Okay, so this is base promoted halogenation. Okay. The two steps are repeated until all the alpha hydrogen are replaced by halogen. Each successive halogenation is more rapid than the previous one because the electron withdrawing halogen atom increases the acidity of the remaining alpha hydrogens, right? This is why
Yeah,
all of the alpha hydrogens are replaced by halogens. Got it?
yes, I got it.
Now, under acidic condition, on the other hand, each successive halogenation is slower than the previous one because the electron withdrawing group halogen decreases the basicity of the carbonyl oxygen, thereby making the protonation of the carbonyl less favorable. Okay, so I think we'll look at the acidic. This is the base promoter, and but we'll come to this. But first, do the uh, problem 9. Okay, and problem 10 also try. Or you can leave problem 10 because we have not covered the kinetics, but still try if you can.
Yeah, sir, done. So
Okay, so tell me.
in 9, I thought it'll be racement mixture because it'll tautomerize and we'll get an alcohol, so then the carbon won't be
Yeah,
carbon.
it will go planar. Okay, that is
Yeah,
the keyword. Okay, it will become planar. Okay, sp2 hybridized, and then
sp2
it can pick
hybridized.
either from the top and the bottom phase, right?
Yeah.
Okay, very nice. Other one?
So in other, I'm not sure, but I thought it's because the rate doesn't depend on which group is getting attached to the nucleophile.
No, that tells us that the rate determining step does not involve the attack on the Cl or the Br or the rate. Rate
Yeah.
determining step is the formation of the carbon ion. Okay,
Okay, yeah, yeah, sir.
right, got it. That step is not involved in the rate. Okay, nice. Oh. Halogenation of the carbon of carboxylic acid. This is Hell-Vollard-Zelinsky reaction. Okay, this is not the hell. But see what is happening. Alpha halogenation is taking place. Just go through the mechanism and let me know if you need me. It's the same thing. First PBr3, it is going to give an acyl bromide. Then from acyl bromide, we are getting an enol, and that enol is going to react, and only one bromine is substituted. See, we talked about this that during the acidic conditions or when there is no base, only one substitution will take place.
Oh, okay, yeah, 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 sir.
Okay, because now if it will protonate. Okay, yeah. So now a bromine is attached. Now you see this protonation is now not good for this because the bromine is already pulling the electrons. Okay, got it. There
Yeah.
it is negative. In the base it is negative, so it is helping. In the acid it is not helping. Huh? It is retarding the reaction. Huh?
Yes, I got it.
Okay. So replacing the see alpha. So replacing the alpha halogen of carbonyl compound. See, now we can do all those nucleophilic substitution reactions. Right?
Oh, okay, yeah, yes, I got it.
Okay.
Yeah.
See, everything is now finished. Huh? Just things are repeating, and we'll do some more questions. So you have to show us that how we can prepare the following compound from the starting material. Huh? So in the first case, we'll do that alpha halogenation, right?
Yeah.
Hell-Vollard Zelinsky, huh? HVZ. See the reagent for this. I'll just do it back. Right.
So what should be the reagent in that case in the question?
A reagent is given, right? We just have to convert. Okay. Here.
Okay, so we can use SHCH3.
Yes, yes. The Br has been replaced, huh?
Yeah.
Got it? First, we simply do that PBr3, Br2, and H2O. We get alpha halogenation. Then we use CS3SH. Okay.
Yeah, and then replace the Br. Yes, sir, got it.
Okay. Write it and send it.
Yeah, writing.
Okay. Because writing will make you remember.
So in the B part, I treated it with PBr3. Then I got
Yeah. Then after that, what is the Gilman reagent doing?
yeah Cu2Li. Yeah,
Okay. Don't forget it is very good reagent. Huh?
yeah,
It is adding carbons. So halogen to alkane, Gilman reagent. Got it?
yes, I got it.
Now forming an enolate reaction, this is not really in the J syllabus, but what they are saying is that when we use the normal HO minus, we'll just get enolate in the proportion of 0.1%. So we use a very strong base, something called LDA, lithium diisopropylamide. So how do we prepare this? This diisopropylamine here, this butyl lithium, so negative, this will pick up and I'll get this. And this is a very strong base, right? So once after it has picked up a proton, it will not give back. Got it?
Yeah,
So that is why we are going to get this 100%. Okay. And here HO minus, it can again pick up proton and it can go back. Huh? But not in the case of this, right? Because the pK, right? pK is 35 and this is 17. So strong to weak. Huh?
oh, okay, yeah, not feasible. Yeah,
Okay. Got it?
yes, I got it. So even the second reaction won't happen, right?
Yes. Second reaction is how do we prepare the LDA, which we are using here.
Oh, okay, yeah.
Okay.
So,
Got it? Because
how
butyl
will
lithium is the strongest base, right?
so will that how will that also happen because their pK is 35 and then butane's pK they've written is more than 60.
It is strong to weak, right?
Oh, okay, okay, yeah, sorry, I was looking at the previous pK and
Okay,
yeah.
okay. No, 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 no. Okay.
Yeah.
So this is what is used, and now you see. Now what we do is, see, we take this LDA, or we can in class 11 to class 12 we'll take the normal base HO minus or something like that, stupid base, and we'll get this alpha hydrogen. This is a nucleophile, right? And from here only I can alkylate it, right? 1 2 portion Br, right? I can do this also only, okay? Or you can do this either way. SN2 reaction, got it? It's a nucleophile, nucleophilic substitution.
Oh, okay. Yeah, yeah, sir.
Right? See, so now we are able to alkylate at the alpha position, right? See, this chapter is reactions at alpha carbon, okay? Okay.
Yeah, yeah, sir. Got
So
it.
everything will happen at alpha carbon. See, the same thing, okay? We can just do, for the sake of simplicity, for example, compare the following representation. So we can also just show it like this. Got it?
Yes, I got it.
And in this case, if we use HO minus, right? So most of the hydroxide will remain as such, and then that will react with CH3Br. Okay, so this we will get, but in not in our NCRT or CBSE, yeah? We will get the same product. Okay, but this will happen actually in the lab. See, when it is picking up the HO minus from here, that is in equilibrium, right? Again, it will pick up,
Yeah.
and again hydroxide ion. So HO minus is present, and this will react with CH3Br to give this as a major product, not as that alpha substituted. Okay.
So the OH and the CH3Br are reacting.
Yes, they are reacting
Yeah,
SN2.
yes,
Okay.
got it.
Okay. So that is why and the same thing is happening. See, yeah, now alpha. So it is picking up that alpha, and then we are right.
Okay, yeah, yes, I got it.
Right. Because
Yeah,
it has become a
that's it.
nucleophile, so nucleophilic substitution.
Yeah. So if we take both these reagents in excess, then will both the hydrogens get replaced?
Yeah. They both the hydrogens will get replaced, but we are just taking stoichiometric amount because we have to make the reaction happen. We
Yeah.
just want
Yeah.
this. We'll also come to that. Okay. Successive replacements will also be there, but we'll come to that in a while. Now, unsymmetrical ketones, how do we do that? So, LDA, this or this, they can be formed. So, which will be major product? So, what is happening is it is a kinetic and again the kinetic and thermodynamic. Which is the kinetic? The kinetic one is where there are two protons to be picked. Thermodynamic one is the where more stable alkene is there, right? Remember?
Yeah, yes, I remember.
Okay. And the kinetic one is where the it will happen. There are two protons, right? So it is easy for it to pick up here. So this is the
Yeah,
kinetic
yeah.
product. This is the thermodynamical product, right? So thermodynamical enolate is major LD at 0 degrees Celsius. So this we get at 0 degrees Celsius, and at minus 78 we are going to get the kinetic one. Okay. Lower temperature we get the kinetic one. So alkylating a carbonyl compound, this you have to do at homework. Okay, I'll just put it. Homework, very important. Okay. This is also very important. Synthesis of aspirin. See now what is happening. It's the Kolb-Schmidt reaction. Phenoxide ion, O minus is coming here, C minus going here. I think we'll cover it later also, so we can skip it for a while. Because it is nowhere this. But yeah, it's important, so I've written it important. This is the same thing, okay? Alkylating a carbonate, see? LDA, and then we use that. Okay. Don't have
Okay,
to.
yeah, got it.
Okay. This again. Ketone and organohalide. Again, this is homework. This is homework. See, cyclohexanon, from cyclohexanon, we have to make this, okay? So, yeah. Now enamine. So enamine are intermediate. See, what are they saying? Enamine. If we make the resonating structures of the enamine, for example, here. Oh my God. Let me change this. This is the enamine, and I'll just draw this. So lone pair will come here, and this. So this is a negative at the alpha carbon, right? Right?
Oh, okay, yeah, yes. So the acidic H is the one.
So the same thing, E plus any electrophile can react. Huh?
Yeah.
Got it?
Yes, I got it.
Okay. Just the same as this reacts. So this is another reaction. You can see. Okay. And acylation, same. This is a nucleophile, so nucleophilic acylic substitution is taking place. Just go through it.
The how is the last step happening? How is that entire thing leaving?
Because it is an enamine, remember, double bond off.
Oh, okay, in a main reaction. Okay, I got it now.
Okay, and relax.
Yeah.
Okay, got it?
Yes, I got it.
Great. Okay, try this also, homework. Now I'll calculating the beta carbon. So it's the same thing, nucleophilic and this. Okay, conjugate product. See now what is happening. Because it's a weak base, so it will add to the beta carbon. Conjugate addition taking place. Go through it.
Okay, yeah, yes, I got it.
Although these are this is not really okay. We'll just skip now Michael reaction. Alkylating the beta carbon by Michael reaction for the moment. I'll just skip it. skip because I just want to get to the aldol. Okay, this is where we have to do. So what happens in aldol is there are two aldehyde or ketone molecules and they are going to give this. So first I'll just jump to the this. See what is happening. First, the aldehyde ketone, it forms a carbanion, right? This is a nucleophile, right? Got it? Yes?
Okay, yeah, sir, yeah.
Right, it's the same thing happening.
Same
Okay,
thing,
first the
yeah.
base
First
is
step of
abstracting the
base
alpha hydrogen
capitalize.
and then it is becoming a
Yeah,
nucleophile, carbanion, right? Now this carbanion is a nucleophile. So what it does, it adds to the second molecule. Got it? Nucleophilic addition. See?
yeah,
And we get this big molecule, a beta hydroxyaldehyde. Got it? Simple nucleophilic addition. Yeah?
yeah. So just going through that.
Mm.
Okay, yeah, sir.
Okay. I've drawn it like that, so you might be getting confused. But yeah, same thing. Got it?
Yeah, sir, got it. Yeah,
See,
same
first
thing,
step we
got
get
it.
a carbanion, it'll add, and this, and we get a beta hydroxy aldehyde or beta hydroxy ketone. If it's a ketone, we get a beta hydroxy ketone. So whenever you see beta hydroxy aldehyde or beta hydroxy ketone, it should immediately in your mind you should be alert about the aldol. Okay,
Yeah,
all ald for aldehyde, all for alcohol. Okay,
alcohol, yeah.
so ketone also gives the same reaction. Okay, so you have to do the 20th. Okay.
So for aldol addition, if they just say aldol addition, then I'll just take the
Alpha hydrogen, make it a nucleophile, add to the second molecule, nucleophilic addition.
yeah, sir, but which aldehyde do I take?
Which alpha hydrogen? This is the one, right?
Yeah. Oh, okay. Yes, I got it.
You and the second, draw the second molecule and add to the carbonyl group. Okay,
Yeah,
got it?
got it.
You can also see this. If you see, same thing you have to do.
Yes, sir, done.
Okay.
Yes, sir, send.
Okay. So retro aldol is something like this. See, just the retro means reverse, right? So it has broken. We have broken the beta hydroxyaldehyde using that. Everything is in equilibrium, so it's like this. See. So actually, we are able to generate the reactants from here.
Okay, yeah, yes, I got it.
Okay, and also we can do like this. I mean, you can break from here. Just keep it green. Just break it from here. Saturate this one. I'll get CS3CHO, and also
Yeah.
convert this to the corresponding aldehyde. You'll get CS3CHO. You can do either way. I'll just put it there that you can break from here. So you have to break it from alpha beta. So on the right hand side, you'll get acetaldehyde. You saturate it, right?
Yeah.
And on the left hand, you know that we have to use two aldehyde or ketone, so you make the corresponding aldehyde. You get it. Do problem 21. At least first part. Yeah, we have class tomorrow, right? Yeah.
Yeah, yes, sir.
Okay, send this to me. Okay.
Yeah, sir. Yeah, just the last part left.
Oh, nice. Nice. Wow, so happy. I'll also populate first and second chapter here.
Yeah, sir. Yeah, done with this question.
Okay, you send it to me and then we'll meet tomorrow. Okay.
Yeah,
I think
done.
I think we should be done by July. In July, hopefully. Okay.
Yeah.
We have already covered the major chapters and yeah, we'll increase the speed. Okay. Yeah. See you tomorrow. Vijay. Okay. Bye.
Thank you, sir.
Okay.